This is the Weather Lounge here at WeatherWorks.
Hi there, everyone, and thanks for dropping by the Weather Lounge. I'm your host, meteorologist Brad Miller, and this fresh podcast comes to you from our WeatherWorks headquarters located in Hackettstown, New Jersey, and made possible by Crew Tracker software. And joining me, as always, here in the Weather Lounge is my celestial co-host, meteorologist Mike Mahalik. Hey there, Mike.
Hey, Brad, your intros just have no bounds, do they? I
Nope.
mean, maybe like the universe a little bit?
Well, they're like endless space, Mike. I can just keep going and going, kind of like my lousy attempt at humor in every podcast.
Right. I hope our listeners are really getting an idea of where we're going with these silly intros that we do
It
have
gives them
at
a
times.
hint. It gives them all a
Yeah,
hint.
gets them thinking a little bit
It's
about
like
what
Where's
what.
Waldo, but in audio and podcast form.
Yeah. But your humor is getting worse. I
I
gotta
know.
say that. And if you need more of these dad jokes, I'll text you my dad's email because he has so many.
All right.
It's so anyway, as you mentioned, celestial in space, and it's a good way to open today's podcast. We have an astronomer joining us on the show. In fact, he's a chief astronomer at the Franklin Institute, and he is here to talk about all things in the universe and the brand new James Webb telescope.
Hmm.
But before we meet him, let's take a short break. Stay with us. We'll be right back.
All right, and welcome back to the Weather Lounge. Today, again, we have a special guest. His name is Derrick Pitts, and he is the chief astronomer at the Franklin Institute in Philadelphia. So, without further ado, Mr. Pitts, thank you for joining us today on the podcast.
Thank you for having me. Glad to be here.
Yeah, no, it's you're our first astronomer to the Weather Lounge. We've been doing this now over 2 years, so I guess that's good news on both our
You've
parts.
missed most of the universe then.
Yes, yes. But tell us a little bit about your side. I mean, you've been at the Franklin Institute now. I think I saw since 1978. Is that correct?
Yeah, this is my 45th year or so at Franklin Institute. It's been a great ride because it's such a fantastic place and there's always exciting stuff to do. So who wouldn't hang out and enjoy that?
Yeah. I mean, I'll tell you, I think I went to a planetarium when I was in grade school. It wasn't the Franklin Institute, but it was somewhere in New Jersey, I think. But I'll tell you, it was just one of those cool things you remember as a kid going to a planetarium and learning about my first time learning about space and things like that. So I mean, of course, I went into meteorology, but it's a field that I guess is almost endless. I guess the way to describe it.
Oh yeah, astronomy is one of those fields that allows you to continue to explore as long as you want to, not only in the physics part, but in all the other associated sciences that are connected to astronomy. I mean, it's chemistry, it's physics, it's engineering, it's mathematics, it's biology, any science you want to think of, including geology, is all wrapped up in there. And I suspect that in the not too distant future, there'll be some archaeology too.
Ooh, interesting. So, so Derek, tell us a little bit about your background. What got you involved? Was there one particular event that, just said, I need to be an astronomer?
Yeah, well, I grew up in the 1960s, and during the early 1960s was the beginning of America's space race for the moon and the expansion of America's explorations into space in general, and that really captivated my attention as a kid, and it was all about the engineering for me as a kid. That's what really captivated me, the idea of rockets and how they work, and anything related to that was the enticement for me. And so I stuck with that. But the realization for a kid like me, an African American kid growing up in an inner city neighborhood, is that I did not have access to those avenues that would get me in that direction of becoming a rocket engineer. So I although I really enjoyed that, I have to say that the other thing that captured my attention about the space exploration part is like space itself. And I discovered in my junior high school years that the universe is a fascinating place for all of those reasons we all think of the universe as being a fascinating place. And I mean everything from the expansion of the universe to black holes to how do stars and galaxies form to the possibility of life in space, as well as just the basic thought of how does it all work and why does it all work? So that really, hooked me into wanting to know and learn more and then eventually get around to sharing what I have learned and understand about the universe with others. Because, ultimately, not only do I want people to have a better understanding of how the universe works and how physics works, but it's really about how all that stuff relates to our life on Earth, our own personal experience with science. And I want people to be able to appreciate the beauty of the universe and how it all goes together like I do, because I find tremendous enjoyment at looking at something that you would normally think is mundane here on this planet, but being able to connect it to something that's going on elsewhere in the universe. I really love that. And I think that other people can derive some joy from that kind of stuff too. So I want to share that.
And I wholeheartedly agree with that. I mean, I've always had an interest myself in astronomy, and I think the thing that kicked me off was the Voyager missions. Back when I was a kid, I
Ooh,
remember
yeah.
seeing those shots coming from you know Jupiter and Saturn, and as they were going out towards Neptune and stuff. And it was just amazing to me that here we sent this thing out there and it's so far away and it's still sending back these pictures. I'm just like, it's amazing that
Yeah.
we were
Yeah.
able to do this.
Wait, wait, wait. Let's put that into perspective now. You know that those spacecraft are still traveling, and they are the most distant man-made objects ever produced. Okay,
That I
so
didn't know.
Right.
they are way out there. I think I calculated the numbers recently for their distances, and their distances are something like, you know, don't don't ding me if I miss it by a few hundred miles, but I think
Okay.
their distances are like 13 billion and 12 billion miles out. Now, that's, let me see, what? Three times the distance to the average distance to Pluto, that kind of thing. It's amazing. But here's the thing that's even more exciting. They still work. And one of the spacecraft is still delivering real science. So let's just compare that to what happens on a really cold winter day. Your car's been sitting for 3 or 4 weeks. You go out, you try to start it, and your car won't start because the battery's dead or something like that. But these spacecraft at 13 billion miles away are still working. That's some pretty good engineering.
And not only that, Derek, I always think about, Mike and I, of course, we're meteorologists, and the extent of our study, basically, or where we forecast, it ends at the tropopause. Basically all everything that happens
Mhm.
with our weather is the troposphere, and maybe goes up
Yeah.
60,000 feet, 70,000 feet
Mhm.
at the most, maybe. And then
Mhm.
you take it from there, and then who knows how far out it goes after that.
Yeah, that's true, that's true, but guess what? There's weather on all those other planets too.
I
On
was
many
gonna
other
say,
planets,
yeah,
let's say.
yeah.
Yeah, 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 there's weather out there, so,
We
in
feel
fact
very minuscule as meteorologists, then, that we're only dealing with 60,000 feet of the atmosphere versus where you take it from there.
yeah, can I get you to give me a forecast for what the weather is gonna be like, halfway down the atmosphere in Jupiter, please?
Exactly. Chance of solar
If it's
storm.
anywhere near the red spot, you're in bad shape.
Yeah.
Oh, yeah, okay, I'll remember that. I'll keep that in mind for my next trip out there.
Hurricane, twice the size as Earth, something to that
Yeah.
effect, that seems
Yeah,
like a
some
good place to be, right?
right, some serious weather. It makes these thunderstorms look like nothing here, right?
Right. Yeah, but yeah, that's I mean, back to those Voyager missions, haven't I heard lately that one of them has exited the envelope of our solar system? Is that correct?
Yeah, such a fascinating story about that. When you talk about weather here on this planet, like you said, we're up to the troposphere here. But if you think about the environment of our solar system, you can actually think of what happens in that space between the sun and all of the planets. You can think of that space as a place where there is there is activity that happens that we call space weather, and really what's happening is that there are these electromagnetic particles that are constantly blasted out from a star, our star in particular. And one of the things we're seeing with these Voyager spacecraft is that they are beginning to reach the edge of the sun's influence of density of those electromagnetic particles at their distances. And so this really interesting signal was coming back from one of the spacecraft, and it sort of looked like there was some kind of signal, then there wasn't. We could detect that signal of those electromagnetic particles and their density, and there was a sudden drop off, right? And then the intensity came back. Then there was a drop off again. And scientists were really struggling to figure out what was going on with this because they didn't understand how it was that there was this variation until they realized that what was happening is that the spacecraft was at the very edge of the greatest density of this electromagnetic particle, flow from the sun, and that what was happening is that that front of electromagnetic storm stuff was pulsating back and forth ahead of the spacecraft and then behind the spacecraft. And that would make this kind of phenomenon happen where it seems to be intense, then not intense. And the realization is that the spacecraft is nearing the edge of our solar system and the sun's electromagnetic field influence on the solar system. Really fascinating stuff.
Yeah, I mean, it's interesting that you put it in the way of a front, kind of like we would deal with the weather. When you have a cold front coming in, you crossing that boundary between more dense cold air and less dense, heated air and warm air. So
Yeah,
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 it's
yeah.
kind of very similar to that kind of thinking.
Yeah, it helps to have, it helps to be able to create this kind of analogy using, mechanisms and models that we already use. We could apply this to what we see in space to some degree, and that makes it easier for people to understand what's actually going on out in space. So it's a fun way to do it.
All right, so kind of like the elephant in the room. Let's talk about the James Webb Telescope. I mean, it's
Big.
big news. It's I mean, we'll get more to space weather a little bit later, but we got to get to this telescope because I mean, I think this thing is amazing. What's going on with this?
I mean, I was blown away when Hubble was released.
Yeah.
I don't even know what you probably have the year better, Derek. But
I want to say 1985.
right.
I'll think about it and we'll see. Yeah, we'll figure out.
But then now this new telescope and the images that I have seen are just spectacular. Um, so wow, I mean, like, how long has this project been in development?
I think people will be amazed when they begin to understand that James Webb Space Telescope has been in development for about 30 years.
Wow.
Yeah,
Really?
a long time. A long time. And a lot of the time spent in the early years was developing the technologies that have been incorporated into the telescope. I mean, like inventing new technologies for the kind of detecting work that the telescope is doing. Because at the time of the initial design of the telescope, a lot of these kinds of instruments did not exist. And so engineers had to invent devices to do what it was that researchers wanted the telescope to do. Now, let's also be candid and realize that later in the development of the telescope, there were a number of delays, built in, not built in, but a number of delays that happened along the timeline of development, for budgetary reasons. And then there were, the other engineering challenges that had to be worked out, and that caused delays. James Webb should have launched, 5 to 10 years earlier than it did, and so and at a much lower cost. But it's the way things go over time. Your prices go up, and sometimes your engineering challenges cause you to take some more time. So yeah, it's been under development for 30 years. Thank goodness they took the time because as we look at James Webb now, and I'm sure we'll talk about this, it's deployed and it's working perfectly.
So who is James Webb? Just maybe some of our audience. I'm not completely sure.
Yeah, that's a great question. James Webb was an early administrator of the agency we know as NASA now. This is very early on in the late 1950s and 1960s. He was an early administrator, and James Webb did a lot to get the Apollo program up and running. He was not the administrator at the time that astronauts landed on the moon, but he was one of those administrators early on that really got the program going. And so, for that reason, James Webb is in that line of NASA administrators that had a significant impact on the agency early on.
So thanks for that description there. I really want to get back to the instrument itself, though, because I know it was somehow they had to fold this thing up onto a rocket, launch it out there, and then it somehow had to unfold, and it has all these mirrors. I think they're gold
Mm, mhm,
plated. I mean,
mhm, mhm. Yeah.
how is this accomplished? And just talk a little bit about that.
Yeah, this is a real origami trick,
Origami.
more so than anything else. The Oriental art of folding paper to make different kinds of
Like those little footballs
figures
we
and
used to
things like
use in
that.
grade school.
Like,
We used to.
exactly, exactly, just
That's
like that.
where
This
it
is just
ends
like
for me.
that.
Just the little paper footballs, but
Yeah,
folding up a telescope is much more complicated.
I'll take it. No, that's about what they did. The situation is that first of all, we have to be able to get this telescope out into space. And that means if we're going to launch it on a rocket, the rocket has to be able to cut through the atmosphere. What size is the payload? How big does the rocket have to be? And if you want to, like minimize the size of the package and minimize the effort it's going to take to get it out of the Earth's atmosphere, then what you have to do is make that package as small as you can. So this was launched on an Ariane 5 spacecraft out of Kourou, French Guiana in South America. And the Ariane 5 is a really dependable rocket that has had a long history of successful launch missions. Arianespace is the name of the French company that operates this launch system. And so at the top of the rocket, in the payload portion, they needed to make this spacecraft fit in the housing, the fairing that would be at the top of the rocket. When you look at James Webb Space Telescope, it is not aerodynamic in any way, shape, or form, right? It's a really odd looking thing. It's about the size of a tennis court. It has 18 hexagonal mirrors, each of which are a little more than 4 feet in diameter. And altogether, they make a telescope mirror that's a little more than 21 feet in diameter. And this makes it the biggest space telescope that's ever been launched by far. So, in order to get this thing into space, what you do is you fold it up into a tiny package, into a very small package, so that it can fit within the fairing housing of the rocket on atop the rocket, so that it can make its trip through the atmosphere in the most efficient aerodynamic manner possible. So what they did was they actually folded all the pieces up. So they take this mirror array, it has two folds in it, so you can fold the pieces on top of each other. And then they have these tremendous sun shields that also roll up and fold up. And as I said, unfolded, this is about the size of a tennis court. So
Jeez.
once you get it folded up, now you can launch it, and that's what they did to get Space Telescope into space. It weighs about 1,500 pounds, which is kind of amazing for its size. And you mentioned that the mirrors are made of gold. Actually, they're made of beryllium, and the beryllium hexagonal segments have a very, very thin coating of gold. It's what's called vacuum deposited on the surface of the beryllium hexagon, and the amount of gold that's being used altogether is 48 grams. Now, if you wanted to know how much that is, 48 grams is about the mass of a golf ball.
I was just gonna say it's like a golf shaft, a really light golf shaft. I mean,
Hmm.
most
A
golf
really light
shafts are
golf
like
shaft.
60 to 70 grams. Yeah, I'm just kind of comparing it
Yeah,
to that.
right?
Wow.
That's how much gold is there. But the layer that's deposited on the mirror is very I can't even describe to you how thin it is. I can use some word about, nanometers, that would be a unit, but I can't make you know how thin that is. But it's vacuum deposited. But it's thin enough, I should say it's thick enough to do the job that needs to be done. And it's a very highly specialized job because this is a telescope that's unlike Hubble Space Telescope in that it works in a totally different energy regime for detecting information about objects deep in space.
Yeah, and I think that is the energy they're looking at is more of the infrared variety. Is that correct?
Yes, and let's just label that clearly for everybody. They're looking at heat signatures from objects. Heat signatures. Now, when we say heat signatures or infrared, that's what we're talking about. Infrared is that heat portion of the electromagnetic spectrum. But let's not get the idea that it's looking for heat signatures of very hot objects. It's actually looking for heat signatures of objects that have a dramatically different temperature than the space around them. And so that's how it detects objects is, the medium of space, interstellar space is cold, near absolute zero cold. So any object that's generating any
Any
energy
kind of
will
heat would show
stand
up.
out.
Yeah.
Yeah, any kind of heat will show up. Exactly. But what James Webb can do is it has the ability to discern very, very small differences between objects or regions or areas of space. This now allows it to produce very highly detailed infrared images of objects in space.
So where does the thin gold plating come in? Does that make it better at finding or detecting that?
Exactly. Yeah. It makes it very much more sensitive to these heat signatures. And that's what's important about both the beryllium that's used for the mirror surface itself and the gold that's used on the surface. This increases the efficiency of the whole system to, first of all, get rid of any excess heat in the whole system itself, the whole telescope system itself, and make the telescope that much more sensitive to any object in space that's generating a little bit of heat energy.
So if we can relate this to any kind of weather, now Mike and I, we deal with satellite photos and satellite loops and images. I mean, and we look at infrared satellite at night, visible during the day. So I mean, what kind of a difference is there between like a weather satellite versus the James Webb telescope? I
Right.
mean,
So weather satellites are looking at, at temperature regimes that are pretty normal, for existence here on Earth. Those temperatures that are important to our existence on the planet. Whereas what James Webb is doing is it's looking at temperatures that are signatures of processes related to how stars are born or how galaxies form or how the temperature difference between um, objects like really protoplanets or even exoplanets orbiting other stars. But being able to do that over an extraordinarily long distance with very, very, very narrow, sort of like viewing windows, if you will. So think of it this way: we look at the moon in the sky at night and we see how big the moon looks to us, right? Well, imagine how big the moon would look, how big the moon would appear to us if we moved the moon 13, well, let's just be moderate and say 10 billion light years away. How big would the moon appear? Well, it would be almost infinitesimally small,
Right.
right? You'd
Exactly.
never be able to see it. But James Webb Space Telescope has the ability, the resolution capability to discern temperature differences between objects at that distance.
wow.
That's
It's
amazing.
crazy.
That's
It's
amazing.
It's
just
truly amazing.
crazy How do you make an instrument that has the capability to
Well,
do that?
you
It's
can just
just
slap on one of
beyond.
those filters now too. That I don't know if you guys have seen that. There's this new filter that it brings all the space planets and everything right up close. I don't know if you guys have seen that yet. It's
Oh
kind of
yeah,
it's kind of
well
neat,
the
but
yeah, the imaging capability of this telescope, the imaging capability is far beyond the imaging capability of any other kind of instrument ever built. So it has ridiculously high resolution, right? And in that resolution, it has like angular resolution in the sense that it can separate, odd tiny objects at extraordinary distances. So it can not only produce very, very clear images of objects very far away, but it can also separate objects that seem to be very, very close together at extreme distances. So it's a miracle. It's a miracle instrument. It just is a miracle instrument.
So I had a question because we were talking about how it's seeing infrared, but when we think about it, we're only able to see with our eyes visible light, which is why it's called visible. So how are we able to see what it's seeing? You know what I'm saying?
Sure. I
Because
do. I totally get it.
it
Right.
doesn't.
So what happens is, here's what happens. The data comes in as grayscale images. So if you have a source that's creating energy at this energy level or at this temperature, it has one grayscale level of intensity. If you look at an object with a different temperature, then it comes in at a different grayscale intensity, right? So now you have these two things together. They're both grayscale. So it's this kind of gray and that kind of gray. Not
Hmm.
very exciting to the general public observer, but for scientists, in the data, the numbers in the data are really what they're after, not the imaging so much. But let's now do something about the imaging so we can see what this data looks like. So this one grayscale image at one infrared value, we're going to assign that a color, and we're going to assign the color red. Now we're going to take, the other grayscale image, and we're going to assign that a color, and let's assign it green. Now we have ways to look at these two different pieces of data relative to each other by temperature, and we've identified colors to tell us which temperature is which color. So now anytime we look across this image, if we're looking for this value of infrared, well, we can see it's this green color. Now we can see how the green and the red, or whatever the other color is, how those things relate to each other physically. And that then helps us to now, you know, get a different kind of impression of what's happening, because we're not only looking at just the raw data of the IR, but now we're also looking at, the physical juxtaposition in a format that satisfies this kind of detection system. And so now we have these two ways of looking at the data that really helps us to tell a story about what's happening someplace. Now that's the simple description.
Well, that's totally fine. I mean, that makes perfect sense. It really explains how we can see that. Um, my other question was, I have a lot of questions for you. I did ruin the curve in Astronomy 101 and
oh,
back at
great,
Penn
Mike.
State University. So everybody looking at their exam scores and they're going, "Oh, who's this guy with the 102% here? He really ruined us here."
Hey,
Um,
questions are where it's all at in science, so I'm fine with questions.
so anyway, nobody liked me in that class. But anyway, uh, so I was curious, how does the James Webb Telescope compare to Hubble or compare to something here that's Earth based?
Yeah, that's a super question. That's a fantastic question. People think that James Webb is going to supersede or replace Hubble Space Telescope, and that's not the case at all. These are instruments that work in different portions of the electromagnetic spectrum. So Hubble works in the visible portion of the spectrum, it works in the ultraviolet portion of the spectrum. James Webb Telescope works in the infrared portion of the spectrum. So these are complementary instruments. This one collects information about this object from this point of view. This instrument collects information about that same object from a different point of view. So now you can put those pieces of information together and get a more complete understanding of what's happening at that object. Now, here's the even cooler part about this. That is that these two telescopes also work in concert with ground-based telescopes that also have incredible image capability as the result of newer technologies that now allow ground-based telescopes to be almost as good, if not as good, as space telescopes. So when you start putting all of these assets together, the radio telescopes, the optical telescopes on the ground, the infrared telescope, the visible telescope in space, the ultraviolet telescope in space, when you start putting all these assets together, they start to build up a picture that's far more complete than any one instrument can give. So they work together in concert with each other to produce the information that scientists want to have to understand how the universe works.
Wow. Yeah, I mean
Yeah, it's very cool.
that is really awesome that everything works together in order to get that completer
Yeah.
picture of everything
Oh
or more
yeah.
complete. I mean, that's wow.
Yeah.
Um,
Yeah. It's not a replacement. It's
yeah,
not a
that's great.
replacement. They work together.
So
That's
how long would James Webb now live? I mean, how long I mean, if this all these other the Voyager and all that stuff, I mean, it's still going. Is this same thing in
Well,
100 years
no.
or?
There are some differences, and here's probably the most striking difference. You know, the Voyager spacecraft and the Pioneer spacecraft. Remember those guys, Pioneers 10 and 11? Yeah, okay. Well, those spacecraft, once they were launched on a trajectory through the solar system, you know, they're going to continue traveling on that trajectory forever unless something disturbs them.
Okay,
You know, they're
that's
out of
kind of what I was
fuel
getting at. Yeah,
essentially. Yeah, they're out of fuel. They can't maneuver. They can't change course. They can't do anything. And if you go by Newton's laws of motion, they're going to continue on their path unless something interrupts their
stop it.
path
Right.
somehow, right? Okay. Now, let's go back to Space Telescope, James Webb Hubble Space Telescope, James Webb. Those devices will suffer failures because number one, their instruments will eventually fail. Hubble Space Telescope has had some issues already, but fortunately, it was placed in an orbit that was accessible by astronauts so that repair work could be
That's
done.
crazy. Yeah.
Yeah, isn't that cool? Just send a repair crew to go fix it. It's
Yeah.
like sending
yeah,
AAA out to fix
Yeah.
Hubble Space
right.
Telescope, right?
Forget about your
Yeah.
car. Let's go fix a space
Hey,
telescope.
let's
All
go
right.
fix the space telescope. Right. Now, James Webb Space Telescope is located, so Hubble is at 400 miles up, approximately, above the Earth. James Webb is 940,000 miles out from Earth. So there are no repair
Yeah,
missions
that's true.
headed out there to fix that. So it had to be built perfectly when it was built and assembled and tested. They had to know that everything was going to work perfectly. Otherwise, you got a $10 billion telescope that doesn't work, just sitting there in space doing nothing. But here's the real kicker for this one. It is that it has enough maneuvering fuel to last about 10 years. So for the next 10 years, it has the ability to maintain its orbital position 940,000 miles away. Now, it's not orbiting the Earth. It's orbiting a gravitational balance point between Earth and the sun that sits 940,000 miles away from Earth. And interestingly, this is called the L2 Lagrangian point. And it doesn't sit exactly at the Lagrangian point, but what it does is it orbits around the Lagrangian point. And together with the Earth, this all orbits around the sun. So here we have James Webb orbiting around the Lagrangian point. Then as Earth orbits around the sun, James Webb and the Earth orbit the sun together as they go around.
See, this is where
That
I get
gives,
lost in space.
yeah, that's
For
exactly
lack
what
of a better
happens.
word,
Yeah,
it's
it's
the
easy.
vastness. It's the
It's easy
vastness
to
of what's
do.
out there and what's not out there.
That's true. It's easy to do, but that's not even very far away. We all know that.
Right.
But it's an important location because at that location, James Webb Space Telescope is positioned where it can best do what it needs to do. It needs to be far away from the Earth so that there are no, sort of like polluting signals that get into the telescope. And in this way, looking out into deep space, it can have as pure a heat signature from these distant objects as possible without the Earth or the Moon or the Sun interfering. So that's why it's where it is.
Great. So, we have it way out there. How far can this thing see? I know I've already seen a picture looking at a galaxy cluster from long ago, or because obviously this, the further you look out, the farther you get back in time. So, like, are we getting close to that Big Bang kind of distance?
Oh, yeah. Oh, sure. James Webb Space Telescope can see back to that era of time. Okay. 13 billion, 14 billion light years away. It has the capability to see back to that era. Okay. But it's not like James Webb can look for a specific point of origin of the universe, right? Because astronomers actually don't know where that point is. What astronomers can see is astronomers clearly understand that there is an expanding, quote unquote, edge of the universe that's rushing outward at a very high rate of speed. We can't see the edge, but what we can see is that the galaxies of our universe, the very earliest galaxies, are being pulled outward by this expansion, in some instances, at a significant percentage of the speed of light. Did you know that there are some galaxies that are rushing outward at rates of 33% of the speed of light? Like whole galaxies moving at that rate of speed. So here's what to do. When you look at that James Webb Deep Field and you see those reddish splotches, these are the galaxies that are at the most extreme distances and the ones that are moving out with the highest velocities, right? So they're just, this is the evidence of the expansion of the universe. So very cool. So now James Webb can see out that far. And what James Webb is looking for is it's looking for data that helps us better understand what the morphology of the universe was like at that time during that era. What was out there? What were the early galaxies like? Can we get a better handle on this sort of chicken and egg thing of, was it the galaxies first or was it the stars first? What was the environment like at that time that allowed the forces that we know of in the universe, gravity, electromagnetics, and the other energies, to sort of form out of what was the primordial force of the universe, when everything in the universe was all back in one small dot of energy, when all of the forces of the universe were one force. What was it about the early history of the universe, that early era of the universe, that allowed for everything to begin to expand and cool and have these forces begin to separate out? That was the weak nuclear force and the strong nuclear force, the electromagnetics and gravity. What was it about the early era that allowed that to happen? Then the big inflationary period, that we now see, manifesting itself as what we have in the universe of all these trillions of galaxies. So, so that's one thing that James Webb is looking for. The other thing that James Webb is looking for is we want to see if we can get a better handle on what some of these exoplanets are like, planets orbiting other stars. What are those planets like? Can we actually can we get any kind of data that will tell us anything about their atmosphere? Because we'd love to know if these planets not only have atmospheres, but what those atmospheres are like. Okay. Now, you guys probably think that we want to know about these atmospheres because we want to understand the weather on those planets. Yeah, but no, sorry. It's more than that. I think it's the holy grail of
Right.
all of us doing, research work in understanding the universe, I think we want to know about the atmospheres because we want to find out how many planets out there are Earth-like planets and if there's any possibility of life.
Yeah, that's the big question in the room. I mean, Brad said the elephant in the room before, but I think that's the biggest one is there other life out there? And I mean, obviously, when you think about the odds of that with how giant the universe is, even our own galaxy, even our local area, it's like there's so many exoplanets out there. There has to be something, right? At least that's how I think. And that's probably what the scientists like yourself are searching for out there. Um, to see that. And I've heard crazy things about exoplanets so far. About, yes, some are Earth-like, but some are like, yeah, raining like molten material, and some are like almost like a diamond, and all these. I'm like trying to wrap my head around these things, because it's such a new notion. And it just doesn't compute really, because obviously we live here on Earth and we know how things work here. So,
Yeah, that's a great way to say that. Yeah, that's a really great way to say that. The physics that governs how the universe operates allows manifestation of what we see here on this planet, for these conditions. And it's great. I mean, it's fabulous. A day like today, for me, one of the things I think is really cool about how the physics manifests things in this environment is, I look out my window and I see the green leaves of the trees against a really gorgeous blue sky. And to me, that's a very satisfying thing, but it's all about the physics related to how the plant generates energy and, how the light of the sun is scattered off the, molecules of the atmosphere that make that the way it is. But if you step off the planet and get out into deep space, physics has the ability to manifest lots of far more exotic things than you ever would imagine would be possible. So, these considerations of some of these other exoplanets as being wildly different from what we have in our solar system, or the manifestation that we see of black holes, as a concentration of gravity, versus mass in one location, that's all part and parcel of what the universe can easily produce. It's not unusual. It's just different for us because out there, physics can do things out there that can't be done here.
all right. I mean, it just, there's so many questions I can ask you right now. I think we're going to definitely need a part two of this podcast, because there's so many things to talk about, from space weather to eclipses to
Right.
the Artemis
Oh,
mission,
oh
um,
yes.
where we're
Mhm.
hopefully sending people back to the moon and possibly even to Mars.
Yeah, I
Um,
would love to have Derek back on. I mean, we were just talking about that, whether we just want to do one podcast, a long one, but I think we and
there's too much to cover. I mean,
right.
to squeeze into one show here.
And
So,
we know Derek has a busy
um,
schedule, and we just we thank him for the time. But before we like wrap up this part one, I want to talk about something that made the news, and I thought it was hilarious. It was a couple of weeks ago, and apparently there was a picture taken of a piece of sausage.
where you going, Brad?
Where are you
Did you?
going, Brad?
I'm being dead serious. It was all over the news. Somebody took took a picture of
Piece of
like a
sausage.
close up of a sausage, like a
Okay.
and they tried to sell it off as a part of the universe. I can't believe nobody heard about this. I know I'm going off script here a little bit. Just Google it. I thought you guys would have heard
Brad,
about
I
this.
don't know. I don't know what websites you're looking at, Brad.
No, it was on like NBC News at night.
How late at night, Brad?
No,
Yeah,
no,
yeah. I
no.
mean, I don't know what's going on here with this question. This is not on the script, buddy.
Oh, wait a minute. Wait. I know what you're talking about. Wait,
Yeah,
this
yeah,
is the
yeah.
chorizo. This is the
I'm
chorizo
sorry, the
sausage
chorizo
thing, right?
sausage. Right, right.
Oh, yeah. Right. This was right.
Oh,
Right. Here's the
See,
quick
I'm not
background
being.
is no, you're not crazy.
Okay.
No, here's the quick background is there was a slice of chorizo sausage
Right.
that
oh, there it is. Yeah.
This
that a
was so
researcher
funny.
actually, put up on the web as being a an image of our sun, I think it was, or another star.
Right.
And the interesting thing is that if you look at the sun or any star in one particular wavelength, then it actually has some characteristics that are similar to what you see in a slice of chorizo. Now, this is not to say that the sun is chorizo, right? Okay.
Right.
But and we actually have this filter at the Franklin Institute that lets you see the sun in this particular way. But what he did was he did something that was really kind of dicey, and that is he suggested that this was an actual photograph of a star or the sun. I can't remember which. And the issue with this, and he meant it to be a practical joke,
Right.
is what the truth is here. But the problem is this person has more than 90,000 followers. And
Ah.
so when you get to that level of sort of, saturation of the market and people following you, they take what you say as
So social media now is and like the old adage they've been saying, if it's on the internet, it must be true. So
yeah, right,
and
right.
it
Thanks.
ran on
That's a
like
short way to say
it
it.
made it to all like the big
The big news
nationwide
outlets and
newscasts and
stuff.
stuff. They actually had to kind of
Yeah.
say, this isn't real, but this is a funny story.
Yeah, yeah. Well, you have to when you have that number of followers, you have a
Right.
huge responsibility, and the
Sure.
responsibility changes, and when you get to that level, and you have to be careful about what you say and what you make jokes of, and if you're going to make a joke about something, you have to be very, very clear at the outset that that's what you're presenting, so people can go along with you, and that's fine. It's great to have humor in science. You just
Mm.
have to frame it properly.
I
So,
just thought something like
no,
that. Yeah.
the universe is not a sausage.
there's there's no there's no parallels to that right now.
The data is not completely in yet, but as far as we know.
Yeah. Well, I mean, like I said, there's so many other things to talk about. I mean, we're talking only about this universe we're trying, and there might be parallel universes or
Yeah, there's
and
another story right there.
I know, and just to think about, how massive that is just kind of blows your mind. And even when you think about the Big Bang, how everything was collected into one spot, like how is that even possible? Like, you talk about the Big Bang, you talk about like the mass of a neutron star or something like that, and it's like you take a spoonful and it's weighs I don't even know how much, and it's or has this much mass. All of that is just amazing to me, and plus how galaxies look like hurricanes. I mean, I don't know, right?
That is
So
true. Yeah.
I was going to say that it's interesting that you talk about scale like that in terms of energy of the universe and how big these things are and stuff like that. When the work that you do is very close to that already, because when you look at the kind of dynamics and the kind of energy that's in our atmosphere and hydrosphere and what the exchange of that energy can be and the scales on which this energy is exchanged and what the result is in terms of weather systems that we see, that's incredible in and of itself, that kind of process happens on this planet. And the work that you do is identify how those energy transfers take place and what the outcome effects are for those of us that sort of crawl around on the surface of the planet. And that's amazing stuff to study right there without even having to go out into the universe.
it is a pretty tall task, put it that way, to try to predict what these things will be doing in the future. And that's always something I like to say to people is like, well, we are predicting the future. That's pretty difficult to do, last I checked.
Oh, you you
So,
are you are daring scientists, and I wouldn't do your job for anything.
yeah,
There's too many variables. There's too many dynamics going on.
right. And absolutely. And unfortunately, we can't measure every little spot of the atmosphere. We send up some balloons to sample the atmosphere vertically. We have satellites and everything, but it's not like we can go out and just measure a 2x4 and say, okay, we just need 13 feet of this, and where it's all good. We make our project. It doesn't quite work that way.
And we got to fight that guy, that person on social media posting maps from 15 days out that's showing 2 to 3 feet of snow along the I-95 corridor. And what about this storm? 2 weeks from now.
Well,
Well, my hat is off to you for being as accurate as you are with all of the stuff that you have to deal with. I can't believe you get it as right as you do
all
for
right.
all of the information that's coming at you. So thanks a lot for what you guys are doing to
Yeah.
at least tell us when it's going to be sunny or not. Thank you.
We really appreciate that, and thank you, Derrick, for being on the Weather Lounge podcast. This was really great.
Yeah, can we invite you back?
Sure, I'd love to come back. There's plenty more for
Great.
us to talk
Oh,
about.
yeah, absolutely.
Oh
We
my
appreciate
gosh.
It'll
that.
be fun.
Yes,
Sure. Oh,
absolutely.
if I can, let's just mention that you should be following the Artemis missions at NASA right about now because there's a lot of cool, exciting stuff that's just about to happen. So
All
if you
right.
can, keep track of it.
We will do that, and obviously, follow you on social media for some good information, I'm sure. And the Franklin
Franklin
Institute,
Institute, yeah.
is a great
Yeah.
place to visit.
Yeah, we'll talk a little bit more about that too in our next podcast with Derrick.
That sounds great. Yeah, let's do that.
That's a
All
great
right.
facility down there in Philadelphia.
Thank you. Thank you. It is.
All right. Thanks for joining us, Derrick. And thanks everyone for listening. Remember, we'll have a new podcast every 2 weeks here on the Weather Lounge. So please, come back and listen again and rate the podcast. That helps push our show forward. And also, don't forget to visit weatherworksinc.com for all we do there with the weather. So that's all for this episode. And thanks again for joining us.